But isoprene is, they think that what plants use isoprene for primarily is thermal regulation of the plant. Because they're like, stuck where they're growing, and then you have like different weather conditions that those plants are in. In some way, that functions as some kind of regulatory, like metabolism type of thing for them. So if you consider, and also it's like the production of it's associated with plant stress, and I think plant stress is also like a weather factor as part of plant stress in general. So with climate change, as plants universally then are under more stress based on how their local climate is changing, then the production of that can change over time as well, which has implications for total hydrocarbon greenhouse gas emissions and further warming that comes from all of that kind of air. So it's one of those little change over problems. So this is like a little verbal summary of the MBA pathway, right? So remember how we did that? We acetylated acetyl-CoA to make acetyl-acetyl-CoA, and then we did the condensation reaction, right? The collation. So we did that, and then we did the reductions. So those are the NAD reductions, and then we phosphorylated it, and then we did the decarboxylation, and we get the IPP, and then there's the isomerization between the IPP and the DMAP, so that you have those in some amount of each of those. Okay, so we got that. So the non-MBA pathway, which is now called the MET pathway. So this pathway actually did not get elucidated until around 2003. The seminal paper on that was from the Pasteur Institute in France. And the way they figure out these pathways, primarily they look at them in bacteria. So you can radio label your compound, so you insert like C14s at specific spots, and then you follow your pathway and you extract your products, and then you look at where your C14 is distributed. So one of the things they realized after they figured out the MBA pathway is they were finding like larger terpenes down the road that did not have the incorporation of C14 like it was supposed to. And people had all these like varying hand-waving arguments about what was going on, but nothing really was gelling. It was really a lot of hand-waving. Then they figured, okay, maybe there's something else going on. And so they did more C14 studies on specific bacteria and figured out this pathway. And most of the enzymes are characterized, and the mechanisms are pretty well defined, but there's a couple of things that are extremely vague and fuzzy, as we'll get to at the end, where they have like no idea how that mechanism works. So it's always something new. All right, so this is like our goal is to make these guys form. All right, so this is like the big overview, and so this is what we're going to unpack and go through this like step by step. But this is what's in the book. So if you're looking to do a textbook, you've got that. All right. So there's our target. So this is the MET. So how are we going to make this? So what you want to do is let's start off like we got two stereo centers. So we need to get the correct stereochemical relationship between the two vicinal stereo centers that have the hydroxyl groups on it. Right? And then of course the CH2OH, we don't care about that. And so also notice that methyl group that's on carbon 3 or 3-methyl. That one, we need to get that methyl group in the correct spot too. So we have like some regiochemistry issues and then stereochemistry issues that we need to resolve. And what we start with are pool starting materials are going to be pyruvic acid and the D-glyceraldehyde 3-phosphate. And both of these are intermediates that are in the glycolysis pathway, which everybody does as part of primary metabolism. So it gets siphoned off then into the secondary metabolic processes. All right. So before we continue with this, I want to talk about this because half the time, like goes in one year and out the other year, and you don't remember anything about what that is. Okay. So big D, capital L is a nomenclature system that was developed in 1881 by Emil Fischer, the same guy that did the Fischer projection. So we'll talk about that too. So the problem was, so just think about like 1881. You didn't know that electrons existed, you didn't know about photons, you didn't know about the atom concept was fuzzy, like it was not well defined as a physical thing, right? But people were doing experiments with sugars. The sugar biz was pretty big deal. And sugars have a lot of stereo centers and a lot of hydroxyl groups. And what they did do is they played with toys. And one of the toys they had was a polarimeter. Because the polarimeter is like, it's an optical instrument, and optical instruments became trendy starting in the early 1800s. So they had like telescopes and stuff like that. Once they kind of figured out some optical stuff. And so with the polarimeter, you put your sample, it's just a tube, and you shine the light through the tube. But if the light goes through a polarizer, so it's all going in the same direction, then if the sample is asymmetric, it's going to change the rotation of that light. So they knew about that, and that was like a gadget, that they had for the day. And it was used in the wine industry a lot, because France makes French wine. And tartaric acid is a naturally occurring substance in wine, and it precipitates out. And that's like the whole thing about how stereochemistry became unraveled scientifically was by looking at tartaric acid that came from nature in the wine versus tartaric acid that you could make in the lab. And they had different optical activities, right? And so then like working with sugars and those kinds of things, that became like an area of concentration. So one of the big problems they ran into was trying to keep track of everything, like especially with sugar. So what Emil Fischer proposed is that he would just randomly name something. So the capital D is based on the fact that, so he just picked the one that when you put the sample in the polarimeter, the light rotated to the right, which is dextrorotary. Right, so he just randomly said, okay, I'm going to call this big D, and it's a nomenclature thing. Now, if I run a reaction on this glyceraldehyde, and I don't involve, so like, they gotta figure out how they figured this out, because they did not know a lot about stereo centers. But it's like, if I run the reaction, so if they run a reaction, like on the alcohol part, then you're not messing with the stereo center, so the absolute configuration would stay the same, because you're not bringing any bonds to that. So then the concept was, if I do those reactions, then I would still, my new compound that I would make would still be a big B. And so that's just kind of how they kept track of what compounds they had. And then they would put those products in the polarimeter and see what direction that they rotated the light. So it was this like weird kind of nomenclature system. And then so that was a long time there between 1891 and 1951. But then once X-ray crystallography came along, then what you did is you would like get a single crystal of your compound, like a really nice one, send it off for X-ray crystallography. From the X-ray crystallography, you can see exactly what the three-dimensional geometry is, and that way you can determine like exactly what it is. And this is how they correlated the RNS nomenclature, right, which that RNS nomenclature came about in the 1930s. Right? That's based on the Cron-Engel Prelog rules, because they realized this D and L thing had to go away, right? It was not systematic enough or covered in a compound. So the D-glyceraldehyde, so now in 1951, once they did the X-ray crystallography, then they could correlate that with the actual RNS nomenclature system, which is what we use today. Right? So if you look at D-glyceraldehyde, like just look at that one, like how fast can you RNS it? That's like a skill set that you learn in OCHEM 1. Right? And the Fisher projections were invented by Fisher to keep track of like all the possible different sugars that you could have, because they knew that carbon was such a big lunch. Right? So if you they knew what the molecular weights were, so they can kind of backtrack from that. They knew how many hydroxyl groups they had, because you can do dehydration and capture the water that comes out and measure that. And so you can figure that out. So then he started drawing them as a way to keep track, right? Because some sugars have like 5 OHs, some have 6 OHs and stuff like that. So better keep that in mind. We're going to do that. All right. So Fisher projections are the cross, and they have. So his original thing was just to keep track of all the different possibilities. But the current way that we use Fisher projections is very specific. So the horizontal bonds are always coming towards you, and the vertical bonds are always going away from you. So if you recall doing RNS, like for stereochemistry in OCHEM 1, you use the Cron-Engel Prelog rules, and you organize all the substituents by order of priority, 1 being the highest priority, 4 being the lowest. You put the lowest priority group in the back, and then you look at the direction of 1, 2, and 3, whether it's clockwise or counterclockwise, and then you make your decision about order S. R is 1, 2, and 3 is clockwise, S is 1, 2, and 3 is counterclockwise. Right, so remember how to do all that? All right, that can be a little bit tricky under certain circumstances. Fisher projections are foolproof because you're taking a 3-dimensional problem and reducing it to a 2-dimensional problem, and the answer is, so the issue is always, is the lowest priority group in the back or is it not in the back? Right? And people develop like little tricks and stuff, and some of those little tricks work some of the time and fail some of the time, but the Fisher projection works every single time. And it's totally foolproof. So what you do to convert from a wedge and dash to a Fisher is you just like step into it. So if you step into it like a wedge and dash, then your wedge is like on your right ear and your dash is on your left ear, and then it's basically, you just like draw what you see, kind of. So here, H is coming towards, CH3 is coming towards. This means, this is a symbol for like benzene ring, a phenyl group behind you, oh wait, behind. So your groups are either coming towards you or going away from you. So it's really clear whether group 4 is in the correct place or not. So if we were going to do this one, or order of priorities, what's the order of priorities? Remember how to do that? Huh? It is the largest atomic, so the rule is it's the largest atomic number at the first point of difference. So what's first? So yeah, so we look at oxygen, carbon, this will be a carbon. So that's one. What about these two? Well, not because it has double bond, because you have to look at like what's bonded to what. So for like this guy going out, it would be HHH. And for this guy going out, since it's like one of these, so say we're here, it would be carbon, carbon, another carbon, sorry. So carbon, carbon, carbon versus HHH. So that wins, so that would be 2, so it's 1, 2, 3, that's 4. All right, so, but H is not going away from us. So if H is not going away from us, then we have drawn a picture of the enantiomer would have H going in the right direction. So all we have to do is figure out the RNS from the Fisher projection, and then if H is in the wrong position, you just reverse your answer. Okay. So this would be 1, 2, 3, so it would be R, but it's not in the right place, so it would be S. So what you can do is do the Fisher projections on LNG. And if, once you get going on these, especially on these small things, you can just do it in your head. Okay, so if you do like the S1, okay, so what's my order of priorities? One, this is going to be 4. And then, so for this guy, this is going to be OHH. And finally, carbon. And then for this guy, it's going to be OOH. You just count this twice. So, right, and then OBH. So that will be 2. This will be going clockwise, but it's a long way, so this is coming towards me instead of going away from me, so reverse it out. And then to do the R, you just do the same thing. so you would apply the same like concept to it. Right? So what you want to be careful about is this DNL thing. So like in OChem, we don't use DNL anymore. It's DDL. Right? It's like archaic nomenclature system from the 1800s. However, non-chemistry fields like biology, they use it all the time. Pharmacology uses it all the time. And then it's still like there's like biochemistry people that still use it. It's like, okay. But what you have to realize is that there is no correlation between big D and big L and optical activity, specific optical activity in a colorimeter, right? And there's no correlation between big D and big L and RNS. So the only way that you can get the RNS and associate it with big D or big L has to do with looking at that crystal and knowing which way they go. So the only relationship between like one big D type compound and another big D type compound is that you can backtrack them all to D-glyceraldehyde. It's just one of those little weird things. All right. So in terms of our little pathway here, we've got pyruvic acid. And so in this first step, we actually have a cofactor. So there's TPP step. So this thymine pyrophosphate, TPP, it is required as a cofactor in this first step. And so you'll see this, the abbreviation for TPP up there. So this is R2, and then all this stuff over here is, this stuff over here is R2, and this stuff over here is R1. All right, so we need that cofactor. So we have something that can function as base and remove that proton, which leaves us with that carbanion, which is going to function as a nucleophile and attack the carbonyl group of the pyruvic acid. So it attacks the carbonyl of the pyruvic acid, and then we get protonation. So this is the carboxylic acid part. This is the carbon that was in the carbonyl. Now it's protonated. The oxygen is protonated, and here's our methyl group. So now we have this whole piece on here. And once that whole piece is on, then we can decarboxylate and eliminate the CO2. Right? So whatever's functioning as base comes along, pulls that proton off, pair of electrons from break this bond, pair of electrons goes over here. So now we have our CO2, and then this bond breaks and the electrons form a pi bond right there. So we decarboxylate and eliminate CO2, and we end up with this enol attached onto our cofactor. All right, so an enol can function as like high electrons can function as a nucleophile, and so now they can attack our glyceraldehyde starting material. That's also from the glycolysis pathway. So the product of that attack, then now we've got this whole piece on here, and we can protonate that O- with the alcohol. All right, now we've got like this bisphenol alcohol situation here. So we can do the aldol reaction goes in the forward direction and the reverse direction. It's like an equilibrium. So when it's in the forward direction, it's called the aldol or the Claisen. When it's going, when you're looking at the reverse steps, it's like the retro. So if we want to break this down, we can do the aldol in reverse. So this is a way to look at it all one step. So base comes along, pulls this proton off. So then we have like the minus, reform the carbon right here, break this bond right here, then curve the electrons out. So that would give us this ketone. And we get our, then we can protonate this guy and we get our cofactor back. So that whole step, those whole steps with cofactor generates this guy. So we've got some pieces on here. We've got a couple hydroxyl groups, we have carbonyl, but we got methyl groups definitely in the wrong spot. So we can work on that. All right. So all of these alkyl things are, they go forwards and backwards. So in terms of taking that product, we can further break that down. And so we can do another alcohol and break that down going backwards, another retro. So, and we're going to talk about what the possibilities are, because if you look at that, you got two hydroxyl groups on there. So either one of those hydroxyl groups are candidates for being deprotonated. So let's just look at this one. So if we deprotonate this guy, then this is going to form a pi bond, and then we break that guy off. So we end up with this species and this species. Right? Protonate that, and then we make our enol. So there is keto-enol tautomerization. There's a base catalyzed pathway, and there's also an acid catalyzed pathway. And then, so you can cover that in OCHEM as well. So, just in terms of base catalyzed pathways, so proton gets removed from the hydroxyl group, reforms the carbonyl, dumps a pair of electrons out on the other carbon. Right? So if you look at that pathway, that gives you this guy. The way that we think about it is the species is a resonance hybrid. Right? So you can have the negative charge on the oxygen, or you can have the negative charge on the carbon. Like once you remove that proton. So if the negative charge is on the oxygen, primarily, that does not necessarily lead to like reaction pathways that definitely not carbon bond forming. You would be forming a bond with that oxygen. The resonance state that has a lone pair on the carbon is the one that leads to the product. So this is typically the product forming resonance state. This one is the lower energy resonance state. Right? Negative charges on the oxygen versus negative charge on the carbon. So oxygen is more electronegative than carbon. So this is one of the dilemmas that you see in textbooks. The agreement is when we are depicting a resonance hybrid is that we draw the most stable Lewis dot structure for that, which would be this one, right? However, this one, that's the most reactive. So in lots of cases, people will draw this because it's mechanistically a lot easier to keep track of. But if you're drawing it as this guy attacking, then it would be typically what you do is you show this step right here where it's reforming the carbonyl, and then the pi electrons do the attacking. So you can do that either way, but you should just kind of know like that different books do it differently, but they're all talking about the same thing. So I just do it this way. So this is the reactive resonance state. All right, So then, the carbanion attacks the carbonyl and aldehyde, and we form our desired product. And this is done, so if you think about what we have to do here, this, these stereocenters have to be set correctly with respect to each other. So that is only going to come from a delivery system, which is going to be the enzyme that's involved, which is going to be a chiral species in order to get that specific stereo. But our methyl group's in the right place and all that stuff is good, right? Now, the alternative approach would be, well, we got that other OH group there on that double bond. So what do we get if we do that? Well, we can remove that proton, and then we get our enolate, and so we have our resonance state with our enolate, and then our carbanion can attack the aldehyde, and then we get this guy, which is not what we want, right? But this happens too. So you have this little soup, this little mixture of like the different products, but then they're all going backwards and forwards. So like this guy's going back into the aldehyde and the ketone, and the other ones, they're going back as well. And so you just have this whole equilibrium thing going, and then as the desired one gets used up in the next step, that just keeps pushing the equilibrium to the right. All right. So the desired stuff, the next step is going to be reduction. So it's 2 reductions in a row, right? So 2 reductions in a row plus a protonation. So the reductions are hydride delivery, which is the NADPH, delivers the hydride, put one on, we put the next one on, protonate the OH, the O minus to the OH, and then you've got your primary CH2OH on there. So now I've got my met stuff. And then I'm going to modify the map. All right, so we're going to modify the map, and in terms of the phosphate groups, having this part on here, this big huge chunk on here, it's going to control how these guys are going to interact in the next step. So we put that on there, modify that, and then we're going to add a phosphate group to this hydroxyl group right here. So the trick about this is this part then is going to help stabilize where this is in space. We have phosphate group on here, and then our intermediate can be put inside. So one of the things that we have to consider is you've got this one can get phosphorylated, or this one, or this one. So which ones are going to go in the desired direction, and it's all going to be based on proximity of the atoms and how they're held in three-dimensional space, so those orbitals can overlap. so just to repeat, so now we have the alcohol on a phosphate group. It's going to attack phosphorus, and we're going to form this ring. So if you look at this ring is 1, 2, 3, 4, 5, 6, 7, 8. So it's a really large ring. The other alternatives are you can have attack. You do this one, and this will give you 1, 2, 3, 4, 5 ring. So the ring strain from a 5-atom ring is going to be higher than the ring strain from an 8-atom ring. So this ends up being like 10% of the pathway, and the other pathway is like 90%. So there's a lot of competition going on in this pathway in terms of alternate different kinds of compounds. Don't know what happens to those compounds, or it just seems like if you're making, if you're running reactions and you're making a lot of extra stuff, that you should be using that extra stuff somehow, or, you know. All right, so once we get that ring made, now this is the part where we're like, okay, not sure how this is going to work at all, right? So you got to get rid of that ring, and all right, so the electrons get delivered to this carbon, and then that carbon-oxygen bond breaks. Now, the thing is, how are you going to deliver those electrons? And whether they're like one at a time, both together, who the heck knows? They have no idea. That whole thing breaks, and so then we would have like this would be a chain out here, the OCP type stuff, and then we also have to get rid of, I'm missing an arrow, we also have to get rid of that hydroxyl group, and then the pair of electrons from this carbon-oxygen bond go into this bond right here, right, to give us a pi bond. So what's pulling that guy off? That's like weird, because it's not even a good leaving group. It can't just kind of come off by itself. So, but it's I don't know, so whether it's concerted, stepwise, you know, but they know that's the product that they get out of it. And you follow that by like C14. All right, so then once you get that guy, the next part is also unknown, right? So they do know that you go through this kind of intermediate. So this is like a delocalized negative charge. But in order to get to that intermediate, you have to pull off that hydroxyl group and just have that stepped off of some kind of leaving group and leave behind a pair of electrons. And so it's just take away the OH, leave behind a pair of electrons, then you would get this. Right? And that's the resonance hybrid, and here's the other resonance state. Okay. So yeah, you know that the intermediate exists as a resonance hybrid, so both of those carbons that have a partial negative charge on them, they can both get protonated. So if they get protonated, you need this, and you get this. So that's how that works. All right, so you put that all together in a single schematic. So this is a summary of both pathways side by side. It's not too bad. So if we have, so the first part on the left, right, is the NVA pathway. We have the acetyl coenzyme A, CoA, and then we're going to acylate it. So we do that in the first step. Then we're going to do like the carbonization part. So now we've got the two pieces put together. And then we do the reduction part, do that. And then we're right here. And then phosphorylate, and then we do carboxylation and elimination, and we get to this guy right here. So other pathway using the other starting materials, so hydrochloric acid and the ketoglycerol. We do the first part where we have the cofactor and we dump out the CO2, and then we get this guy, and then we do the reduction, step 1, step 2, all the coordination, and then we get our desired regioisomer and our desired stereoisomer, and then we can phosphorylate, make this ring, and then the unknown part, 2 arrows with nothing written on them, like mystery reaction. We end up essentially doing we do an elimination and make that gene out of that. Right? And so these 2 pathways, like in the plant, so the MBA part takes place like in pretty much every cell, and the MET pathway only takes part in the chloroplast. So that's the part, those are the cells that do the photosynthesis part that are on the outside of the leaf. Right? And so now what they think is that there's crosstalk between those 2 pathways. There's like, the more you learn, the more you realize what you don't know, you know? That there's some kind of crosstalk, and so if like one pathway is stressed and can't produce enough, the other pathway picks up and whatever, but they're trying to figure that out in terms of how they would communicate chemically, you know, with each other and stuff like that. So that's pretty much all I have to talk about today. Yeah. I don't think they know. So you know what's really weird right now? So isoprene, it's like used like in the polymer business, you know, to make all these polymers. So you know, we're rapidly using all petroleum sources, and only like 5% of it goes to chemicals anyway, 95% goes to production. And so now what they're trying to do is get bacteria to grow isoprene. Right? So what they're doing is genetically engineering to like cut through these pathways to get the pathways to just like produce more stuff, so that the isoprene would come from biological systems that would then feed into like that chemical feedstock. So they're working on that, and which is kind of like, you know, crazy. So in terms, and then the other thing is, because the MET pathway is not like in animals or humans or anything, is they're looking at seeing if they can figure out inhibitors to different steps in that pathway, because it's like there's various like bacteria that are nasty for people, like malaria is one of them. So that if they can figure out how to stop that pathway and shut it down, then that it actually will kill the organism. So it's required somehow for the organism to live. Yeah, yeah. So that's kind of the route that we're taking for that as well. But, you know, how everything just kind of all fits into it. So, anyway. So next Tuesday, so that's like, so once we get it like the next 3 weeks, like for time, which is the fun stuff. All rearrangements. So, we get out early today.